Okay, so Bayes' theorem is more on conditional probabilities. It's used when you want to switch. It says the unknown event and the given event. And we'll see probably the examples that we can relate to most are like drug testing, testing for a disease. So here's like the official formula, and I'll give this formula to you on the exam. You don't need to memorize it. But we'll see a way where we can do stuff where we maybe don't have to rely so heavily on the formula. So it says in drug testing or in testing for a disease, there's always the chance of the result being a false positive. The test comes up positive even though the person has not used the drug or doesn't have the disease. And then there are also like false negatives. It's easy to test for false negatives because you can, like, especially like if they do animal testing, you can give the animal the drug. You know they've had it. And so then if you give them the test and it comes back negative, you know that it's a false negative. But false positives are, so the test comes back positive. That, I guess with animal testing, I guess it's still, again, relatively easy to test. But in the real world, like, you don't know whether the person, I mean, that's why you're giving them the drug test, right? So what they do to come up with these false positive and false negative rates is they do a very controlled experiment where if it's a drug, they're testing for a drug. If it's like they might do animal testing and they'll give a large group of animals the drug and another large group of animals won't get it, and they'll give all of those animals the test, and so they can see the percent of false positives and false negatives they get. So then when they put this drug on the market, then they can say, here's the rate of false positive or false negative. So then if the employer is giving an employee a drug test and the test is positive, then they say, well, there's a whatever percent chance it's a false positive. So we want to know now what's the probability the person really did use drugs given that the test is positive, right? So it's like we want to switch. Like, so in the animal testing, they say, what's the probability the test comes back positive when we know the animal has been given the drug, right? Because they've controlled whether the animal gets the drug or not. So they want to figure out what's the probability the test correctly identifies the presence or misses it. So they can get those rates. Now in the real world, you switch. You know what the test result is. You don't know what the person's behavior is. So we're switching like the thing that comes first and the thing that comes second. And this was when they talk about confusion of the inverse, right? When you switch the conditional event. When using Bayes' theorem, we'll encounter two different types of problems, those for which results are given in a table. We have an example of that on the back page. And one where we're just given the information in paragraph form. We only know the probabilities of certain events. If the problem is in paragraph form, it's often easiest to arrange the info with a tree diagram. So if we're given it in paragraph form, I would use a tree diagram. And then we'll worry about using that formula. So it says if the information is presented in a table, we can use one of the following formulas. Well, this was our formula for conditional probabilities before. The probability of A given T, remember whatever comes after the bar, that's how we get our new denominator. Okay, so the first problem we're going to do is in paragraph form, so we don't get a table. Suppose that a company claims its test is 98% accurate in testing a performance-enhancing drug, which means it will correctly detect the presence of the drug in 98% of users. Suppose also that the company reports that its test has a false positive rate of 5%. So false positive means the test comes back positive even though the person hasn't used the drug. A university recently received a tip that 12% of its athletes are using this performance-enhancing drug. The university begins testing the athletes, and John Doe tests positive. John swears he has never used the drug. What is the chance that he is telling the truth? And we'll have space to do this problem on the next page. So first of all, which setup applies to this problem? Table or tree? Tree. And then it says use symbols to express the event that John is telling the truth. So I'm going to define 4 different events, first of all, and then I'll use symbols, which is like probability, conditional probability, to write the event that he's, or the probability, I guess, that he's telling the truth on the next page. So there are 4 sort of things we need to worry about. There are 2 outcomes for the test. And so I talked about this briefly before. I'll do T plus means test comes back positive. T minus is the event that the test comes back negative, and I'm just going to use quotes. And then I'll do D plus and D minus. So the T is for test, the D is for drug. And you could also use D for disease if you're testing for a disease. So D plus means the person has used the drug. And D minus is the person has not used the drug. I'm going to change the word event to probability because that's what we're trying to find. Use symbols to express the probability that John is telling the truth when he says he's never taken the drug. So this would be the probability of something given something else. What's our given here? What information do we know?
Tested positive.
Right, he tested positive. John took the took the test and it was positive. So that's the given. Now, if he's telling the truth, what should go here? D minus, because he says he's never used the drug. So we want the probability of D minus given T plus. And then I just don't want to flip back and forth, so I'll leave this up here, and I'll do mine on scratch paper, but you should do it on the back of yours, because you can just refer back up here to see what all of these things are. So when we do a tree diagram, we always start out with this, like, just a starting point. And you have to focus on one of the events. You either have to focus on the test or the drug. And the thing that you start out with, it has to be information that you have about the population. So do we know what percent of the population has a positive test? Or do we know what percent of the population has used the drug? Right. They said they recently received a tip that 12% of its athletes are using the drug. So that's what we know about the population. So we're going to start out with our branches dealing with the drug. So it's either D plus or D minus. And then along those branches, we want to put the probability of each. So what's the probability a person has used the drug? And we'll do it as a decimal. 0.12. So what's the probability a person has not used the drug? 0.88. You just do 1 minus 0.12. Right? So if 12% are using, 88% are not using. So now, well, there's only one thing left, but this person has used drugs. They could get either a positive test result or a negative test result. Same thing with the person who hasn't used drugs. They could get a positive test result or a negative test result. And now we want to figure out what's the probability of that. So what's the probability? So let's see. We've used the 12%. So we're going to have to use these other, oh, I guess there's just a 98 and a 5%. So we're going to have to use those somewhere in our tree. We just have to figure out where they go. So say I call, for now, say I call this branch 1, this branch 2, this branch 3, and this branch 4. And you tell me, where does the 98% go? Right, branch 1, because it says it correctly detects the presence of the drug in people who use it. So we're looking at people who use it, and the test is correct, which means it comes back positive 98% of the time. So this is 0.98. So what does branch 2 have to be? 0.02. Okay, so now we've used the 98%. The other percent they give us is 5%. That's a false positive rate. So where would the 5% go?
3.
Branch 3. False positive. Here's the test is positive, but it's wrong because the person never used it. So a 0.05 goes here, which means branch 4 is 0.95. Okay, now our tree is done. So now I want to list like the outcome and the probability. And there are like 4 places where we could, right? So I could either go this route, that would be the first outcome, which is the person uses drugs and the test is positive. And this is sort of like that fundamental counting principle, sort of. It's just with probabilities. Step 1, we've chosen a person who used drugs. Step 2, we give them the test and it's positive. So we just multiply those 2 probabilities together. So 0.12 times 0.98. So 0.1176. Okay, and now we're going to go, here's another ending spot, which means we went this route. And there, it's a person who uses drugs, and the test came back negative, and we just multiply those probabilities together. 0.12 times 0.02, 0.0024. Okay, we could have ended here, which means we went this route. So D minus and T plus. And we just multiply those probabilities together. 0.044. And then last route, D minus and T minus. So it's 0.88 times 0.95. So 0.836. Okay, so now I've listed all possible outcomes. What can you tell me about these 4 numbers? They should add up to 1. If they don't, then you've made a mistake somewhere. So I'll just check quick. Okay, they add up to 1. Okay, so remember, we were trying to find the probability of D minus given T plus. So remember, the thing that comes after the fraction bar, or the conditional bar, goes in the denominator. And then the numerator is, so now we're only selecting among the T plus people, and we want the D minus. So we just need the probability of D minus and T plus. So now the numerator, d minus and t plus, we have that as one of our outcomes. D minus and t plus is 0.044. But now the probability of t plus, there's more than one way to get a positive test result, right? You could get a true positive or a false positive. And I just said a true positive or a false positive. Or means what? Addition, right? So for the t plus, we look at all of the things that contain t plus, and we add those together. So 0.1176 plus 0.044. And now when we do this on our calculator, just remember, put the denominator in parentheses.
So why would you include basically, oh, I suppose, since it's the drug, rather than like just like the T itself, like the 0.98?
Because we get positive test results for people who don't use drugs too.
So we have to include the drug though, is that why we're adding the 0.116 and the 0.04?
Oh, you mean why don't I just have probability of D minus? Like why do I have this and T plus there?
Like on the bottom portion where it's just the probability of T positive.
Well, that's, I mean, remember the thing that comes after the conditional probability, that's just where we get our denominator.
Why aren't we using like just 0.98 and 0.05 rather than?
Oh, because it's not, well, first of all, what if you did 0.98 plus 0.05? What would you get?
More than one.
Yeah, you get more than one. You can't have a probability being more than one. Right?
Isn't this when we're minusing something? Additional, whatever plus whatever minus whatever.
Well, that's if we had or, right? So the addition goes with or, but I mean, you could think about the subtraction, but we only had these two things that involve T plus, and they are mutually exclusive because either the person does use drugs or they don't. You can't have somebody that uses drugs and doesn't use drugs, right? So we don't have to worry about the intersection. And yeah, the probability of T plus, you could never have, it's a probability. It can never be bigger than 1, right? So that's why we can't just add these two. Yep. Okay.
So we just add the bottom one stuff?
Right. Yep. 0.044 divided by, and then parentheses, 0.1176 plus 0.044. So 0.272. So there's about a 27% chance that he's telling the truth. So that's why, and this kind of goes back to that 10 boys, 10 girls. That's why a lot of times if you test positive, they give you the test again. Because it's not that unlikely, 1 in 3 chance that he really does not use it. So if they give him the test a second time and he really hasn't used drugs, then it would be, well, this is the probability for it happening once, and then so for happening twice, I would have this probability times that probability again. And now there's only a 7% chance, right? So and then if you did it a third time, it would be even smaller, right? So times 0.272. So if you keep testing, so now it's a 2% chance. So if they really argue, yeah, you can, or if the employer or athlete or whatever argues, and you should, but the thing is, if you get 2 positives in a row, then it looks really bad for you because it's less and less likely. Okay, so that was a tree diagram, and then now we're doing one with a table. So what is the probability that an individual was in the 22 to 29 age group given that he or she responded? So here, how they gave us the table is they gave us basically within the age group, what's the probability that somebody responded? So they just want us to switch it the other way. So we want the probability 22 to 29 given responded. And usually if I have information in a table, I'm not doing probabilities anymore. I'm just going to do responded goes in the denominator. So the number who responded. And then in the numerator are the 22 to the number of 22 to 29 people who responded. So I need to get totals here, right? So I definitely need the total for the number of people who responded. And how am I going to get that total? Right, add up everything in this top row. So that's where I'm going to get my denominator. So I get 1,049. So that's my denominator. What's my numerator? 255. Okay. And so 255 over 1,049. So about 24.3% or 0.243 for the probability. Okay.
I like the table better.
Yeah.